This is lesson 14, Hess's law. So Hess's law says that if a reaction is carried out in a series of steps, the change in enthalpy for the overall reaction equals the sum of all the enthalpy changes for the steps. So that change in enthalpy does not depend on the number of steps or the pathway that you take to get there. And Hess's law makes it easier to calculate energy changes that are difficult to measure, for example, big combustions. So here's an example of a Hess's law problem. Calculate the delta H, or the change in enthalpy, for this reaction. So carbon plus hydrogen forming C2H2. Given the following chemical equations and their respective enthalpy changes. So here I've given you 3 different equations and the change in enthalpy for each one. And you can see that none of these 3 is the equation that we want. However, what we can do is add these equations together to get the reaction that we want. So we can see that we want carbon on the left. So the only equation that has carbon is the second one. But we want 2 carbons on the left. So what we're going to do is multiply everything in this equation by 2, so that we have two carbons, 2 O2s, 2 CO2s, and if we do that, remember that we have to go back and multiply the delta H by 2, because if we use twice as much carbon, we're burning twice as much carbon, we're making twice as much carbon dioxide, so we're producing twice as much heat. The next thing that we're going to look for is this hydrogen, because we also want hydrogen as a reactant, and we can see that the only equation that has hydrogen in it is this last one, and we only want 1 hydrogen, and so this equation is good because it only has 1 hydrogen. So the next thing we do is write that equation out with its delta H, negative 285.8. Now the last thing that we need is this C2H2, and the only equation that has it is this blue one up top, but you can see it's on the wrong side. So what we have to do is flip this so that the products are on the left and the reactants are on the right, because we want the C2H2 on the right. And so if we flip it, remember we have to change the delta H, the sign, so it changes to positive 1299.6. And now what we're going to do is we're going to add these equations together. So we're going to cancel anything on the left side of any of these arrows that's the same as anything on the right side of these arrows. So we can see, for example, that we have two CO2s, 2 CO2s. And we also have 2.5 oxygens and 2.5 oxygens. And finally, we have a water and a water, which will cancel. And when we've canceled everything out, if we just circle what's remaining, we have 2 carbons plus a hydrogen and a C2H2, which is what we wanted in red to start with. So now that we know that our equation is going to be correct, all we have to do is add together our delta H's, and we will get the overall delta H for this reaction, which is 226.8 kilojoules. An easier way to use Hess's law is using enthalpies of formation, which are symbolized delta H with a little f. So enthalpies of formation are the enthalpy changes when a compound is formed from just its elements, its pure form. So that F stands for formed. And the elements have to be in their standard state. So the standard state of an element is the form that it would be found at if you were just to go outside and find some of the elements. So it's their pure form at atmospheric pressure, which is 1 atmosphere, and the temperature of interest, which is usually 298 kelvins or room temperature. And the standard enthalpy of formation is the change in enthalpy for the reaction that forms 1 mole of a compound from its elements. And all of those substances have to be in their standard states. So the units for delta H's of formation are always kilojoules per mole. Now, if you have the most stable form of an element, for example, carbon is usually found as a solid, hydrogen as a gas, oxygen as a gas, then the delta H of formation is 0 because that's how it is. It's always found like that. And so it doesn't need to be formed. It's already formed. So its delta H of formation will be 0. So here's a chart that's similar to the one that you have in your book for delta H of formation. And you can see all of these compounds forming from their elements, and these are the enthalpy values. So here, for example, is carbon, and we have carbon diamond, and we have carbon graphite. And if we look back, diamond has an enthalpy of formation of 1.88, meaning that in order for the formation of carbon diamond to occur, the enthalpy changes by 1.88, meaning it's endothermic. Heat must be added. However, you can see graphite is not on this table because graphite is how carbon usually exists in its pure form, so it does not need to be formed. Okay, so here's just a few other compounds. You can see that elements, for example, have a heat of formation of 0, so graphite, oxygen, hydrogen, nitrogen. Positive enthalpies of formation mean you need to add energy to make them, and negative enthalpies of formation means the energy is actually released in order to make those compounds. So here's an example. For which of the following reactions at 25 degrees Celsius would the enthalpy change represent a standard enthalpy of formation? So the first, we're forming 1 mole of sodium oxide, so that's the first requirement. You're only forming 1 mole, so that's good. And we're forming it from sodium as a solid, and yeah, sodium exists as a solid in its elemental state, and oxygen as a gas. So yeah, this one would be a standard enthalpy of formation. The second one, you have potassium as a liquid, no, potassium as a solid, plus chlorine gas, forming 2 moles of potassium chloride. So that is not a standard enthalpy of formation because A, you're forming 2 moles, and B, potassium is not a liquid. And the last one, you have sugar being broken down into carbon diamond, which is not how carbon is usually found, plus hydrogen gas and oxygen gas. Now, are we forming sugar? No, we're breaking it apart. So again, this would not be a formula for the standard enthalpy of formation. So, if we want a shortcut to Hess's law, we will use the following formula. To find the change in enthalpy of the reaction, all you have to do is add together the moles times all the heat of formations for the products, minus adding together, before you subtract, the moles times all the heats of formation of the reactants. So this equation simplifies Hess's law, so you don't have to do all that switching and multiplying and adding together and canceling out. So here's an example. Calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide and water. So all I've done is list some standard enthalpy of formation, for example, benzene, oxygen, carbon dioxide, and water. And now we're going to have to write a balanced equation for this reaction. So remember, combustion, you add oxygen. Then we're going back to balance. Okay, now we have to take the sum of the moles times the delta H of formation of the products minus the sum of the moles times the delta H of formation of the reactants. So our products are going to be 6 moles of CO2, so 6 times the delta H for CO2, plus 3 times the delta H for water, minus, now we're on to the reactants. So in our reactants we have benzene, and we only have 1 mole, so 49, plus oxygen. And remember, oxygen is found as a gas, so its delta H of formation is just 0. So when we plug this into our formula, we're going to get a delta H of negative 3,267.4 kilojoules. Okay, here's one last example using Hess's law. So the problem states the standard enthalpy change for the reaction calcium carbonate goes to calcium oxide plus carbon dioxide is 178.1 kilojoules. From the values from the standard enthalpies of formation of calcium oxide and carbon dioxide given in the table, calculate the standard enthalpy of formation of calcium carbonate. So if we look in our chart, we can see the delta H of formation of calcium oxide is this, and the delta H of formation of CO2 is this. But we don't know the delta H of formation of calcium carbonate. However, for this reaction, they tell us that the delta H equals 178.1 kilojoules. So if we plug in the products minus the reactants, we don't know the reactant, but we know that we have 1 mole of calcium oxide and 1 mole of CO2. And so when we plug those in and add them together and solve for delta H of formation, we get a delta H of formation of calcium carbonate. We get a delta H of formation of calcium carbonate equal to negative 850.9 kilojoules.